All right, in this video we're going to talk a little bit more about how we model solids. So in the last one what we did was talk about atoms and how atoms are bonded together and how we can think of those bonds as springs. So here what I have is a cubic array of atoms connected by springs. This is our way of thinking about a solid. So you have each of these atoms, they're all interconnected. You pull down on the bottom and these guys all stretch. Right? And in the limit of massless atoms or a massless wire, where these atoms are very small compared to the load that you apply to the bottom, the stretches of all of these bonds are roughly the same. And so using that, we're going to try to understand what happens when we attach these things end to end and side by side. So by end to end, I mean if you attach a couple of atoms to let's say a ceiling here. Oop, other way around. Right? So these would be connected end to end. They're going to stretch the same amount. And so we might think of this as having a particular interatomic spring stiffness. And we want to try to understand what happens if we consider the stretch of the entire system as one big spring with an effective spring stiffness. When we're talking about side by side, what we're looking at is if we have two such springs that are attached next to each other like this, but they're both attached to the same mass, right? So each of these has their own interatomic spring stiffness. But we want to model that as a single spring with some other K effective. And so we're going to build both of these two models. We're going to try to understand what happens in this case, what's the effective spring constant that we get for end-to-end springs, and what's the effective spring constant when we have side-by-side springs. That's going to help us add up all of the contributions of these springs to figure out what happens when we actually pull on a wire. Now the full derivation is given in the notes. What I'm going to try to do in this video is just to talk about end-to-end and side-by-side, and then you can use the notes to figure out sort of the rest of it. So we'll first look at the idea of connecting springs end to end. So let's say your interatomic spring stiffness is 100 newtons per meter. Let's just make it really simple. Now, if I attach a mass that has a weight of 100 newtons to the end of such a spring, right? I can tell you exactly how far this guy stretches. So by using the momentum principle, we know that the change in momentum of this mass is going to be 0. So therefore, the net force that acts on that mass is 0. And so the spring force that's a result of this bond is equal to the weight of this mass. And so the product of those two, the spring constant and the stretch, is equal to the weight. So we can calculate exactly how much the spring stretches. It's the weight divided by the spring constant. So that's 100 newtons divided by 100 newtons per meter, which tells us the spring stretches 1 meter. Now our observation is if we attach another spring to this, right? So if I get rid of this mass, I put another spring here of the same spring constant, and I attach a 100 newton mass, this is going to stretch by 2 meters. So let's try to understand what happens if we were to replace this system of 2 springs and 100 newton mass, which would stretch 2 meters, with a single spring with some effective spring constant that also stretches 2 meters. The key here is that we're modeling the 2 springs as a single spring, but they have the same stretch. So if we do that, we know that the momentum principle tells us that there is no change in momentum of this 100 Newton mass. The net force is therefore 0. So the spring force for this new spring is equal to the weight of this object. So the spring constant, K effective, times this stretch, S, is equal to the weight. From that, we can determine what our new K effective is. It's just the weight divided by the stretch, which in this case is 100 newtons divided by 2 meters, which is 50 newtons per meter. So evidently what happens is that if you have two springs connected in series like this, which is what this is called, the effective spring constant, if you model them as one big spring, is that you have a floppier spring. You have a spring with a lower spring constant. It stretches more. We can generalize this, and I'm not going to go into many of the details here, but you can generalize this to a formula which tells you if you have multiple springs in series how to add them up. 1 over the effective spring constant is equal to 1 over the first spring plus 1 over the second spring plus 1 over the third spring, and so on. So this is in general how you would add these up. We can look at our situation and we can see that that actually works exactly. So if we have 1 over K effective, each of our spring constants was 100. So 1 over 100 newtons per meter plus 1 over 100 newtons per meter is 2 over 100. And if we take the inverse, we'll get that our K effective is 50 newtons per meter, which is precisely half of each of the individual spring constants. So this is how springs add end to end. Let's talk about how they add in series. It's slightly different because in that case you have two springs that are supporting the same load and therefore stretch the same amount, but they do it in just a slightly different way. So when you have them side by side, let's say you have a ceiling here, you have one spring and another spring. They're attached to again, let's say 100 Newton mass. Both of these have a spring constant that's equal to 100 newtons per meter. Now if they're attached like this, this block will stretch them both by the same amount. But our free body diagram for this is slightly different. Here's that mass. There are two forces pulling up. One due to the first spring, one due to the second spring, and then we have the weight of the object pulling down. So if we look at the momentum principle here, we know again that there's no change in momentum because this thing is static. So the net force has to be equal to 0. So the spring forces, both of them, must be equal to the weight of the object. So in that case, what we find is that each of these interatomic spring stiffnesses times the stretch is equal to the weight. So we can figure out the stretch, how far these two springs stretch based on this equation here. So that's the weight divided by twice their spring constants. So that's 100 newtons divided by twice 100 newtons per meter, which is a half a meter. So when you have two springs which are called in parallel, it turns out that they only stretch half as much when they're both the same spring constant. So we can model this again as a single spring with some effective spring constant that stretches the same 0.5 meters. And we can determine what that effective spring stiffness is. So again, the change in momentum of this guy is 0. That implies that the net force acting on this 100 Newton mass is also 0. So the spring force is equal to the weight force, meaning that the effective spring stiffness times the stretch is equal to the weight, so that the effective spring stiffness is the weight divided by the stretch, which is 100 newtons divided by 0.5 meters, which gives you a spring stiffness of 200 newtons per meter, the effective one. So when you have two springs in parallel like this, what it turns out that you get is it's a stiffer spring that you have as your model, right? So if you have a bunch of these in parallel, you get stiffer and stiffer springs. So there's this trade-off in this idea of having chains of atoms between the ones that are in parallel, which provide you with a stiffer spring, and the ones that are in series, which provide you with a floppier spring. So finally, just to pay close attention to this, you can generalize this as well. The effective spring stiffness for springs in parallel is the sum of the springs that are in parallel. K1 plus K2 plus K3 plus so on and so on. So these two models, the side-by-side and the end-to-end models for spring stiffness, are going to be incredibly useful for understanding how we stretch very large macroscopic objects.